might want this. Brief trigger warning. This talk does not contain a single line of Scala code, so if you were expecting that and maybe end up throwing tomatoes at me, make sure to include heirlooms tomatoes so I can make a great spaghetti sauce at the end of this. Right, it's August 2017, and Xiaowen has a problem. She needs to know what Netflix titles people are talking about on social media, and what are they saying about them? So the good news is Xiaowen has a superpower. She's a data scientist. And so she sets out to build some models using Python NLP techniques. We're going to skip to the part where she has a model prototype working in her local development environment. Because up till now, it's been a magical journey through fairyland with feature engineering and exploratory data analysis and choosing her model parameters and so forth. What she doesn't realize is that it's about to get dark because Xiaowen needs to get her models into production. And the first thing that she realizes is that she needs to scale her models up to the full data set and not the sliver of data that worked on her local development environment. So she realizes she needs some compute resources. Xiaowen goes to her friendly software engineer, Anu, who says, that's no problem at all. We have a compute resource orchestration system called Titus. It's even an open source project, and it's a lot like Kubernetes. So all you need to do is create a custom Titus executor, farm out your work, and then bring it all back together when you're done. So Xiaowen's a bit daunted, but she perseveres and digs into the documentation and writes a custom Titus executor. And then she realizes what her next problem is, which is she can't get the data to load very quickly on all of these compute nodes. Going through these SQL interfaces has all kinds of challenges, either memory challenges or concurrent job challenges. So again, she goes back to Anu, and they work together for a week, and they get data access running at a reasonable speed. So now she has the full model running on the full data set, but that's not enough because she needs to train the model on a regular basis, which means she needs job scheduling. So once again, she goes to her trusted partner, Anu, who says, hey, we have this job scheduler. You just need to read the documentation, figure out how to do your job configuration, and get it scheduled. So once again, Xiaowen goes and figures all of this out. And she's done, right? But then her boss reminds her, well, we're not doing machine learning just for the sake of machine learning. We actually need to get this into a business application. So enter the web developer who's writing the business application, who Xiaowen approaches and said, I need to get my model in here. And the business application developer says, no problem, just give me a REST endpoint for your model. REST endpoint? So she again figures out how to write a basic Flask app, and that takes some time. Okay, so she's done, she can celebrate, she can move on to the next project, and it only took 4 months. Not bad, right? Except she's not really done, because now the model's in production, and now she has to think about DevOps for the model. What happens if she retrains and there's a problem, right? How does she do historical backfills? How does she continue developing this model while not messing up production? So I'm telling you this story not because it's unusual or because it's sensational, but instead because this is the everyday experience of your average data scientist. In fact, how many of you have similar stories? Okay, a few people. I'm not just making this up here. Let me just retell the story very quickly. So Xiaowen needs to build a model. In order to do that, she needs a data warehouse. She needs compute. She needs a job scheduler, versioning of her data, collaborative tools, model deployment, Oh, and then she can think about feature engineering machine learning libraries. And now she's ready to have a fantastic intellectual conversation about monads and type classes and lambdas. No, not just kidding. She actually has to spend some time thinking about the actual work of creatively coming up with a model to solve the original problem, which was understanding social word of mouth around Netflix titles. So the key observation here is, when you think about it, the lower down the stack you get, the less the data scientist actually cares about any of these details. That's kind of depressing, right? Because we just went through this story where she spent most of 4 months dealing with all of that stuff. There's a good news, though, which is that the lower down the stack you go, the more leverage you can get out of building infrastructure. So this is exactly why we built Metaflow, which was designed to be very opinionated about things at the bottom of the stack that scientists don't care about, and very unopinionated about things toward the top of the stack that scientists do care about. They do care about working in a development environment that they're familiar with, Python or R. They do care about being able to use the models and the implementations of those models that matter most. They don't want to be forced necessarily into using TensorFlow. Maybe they want to use PyTorch or XGBoost or VopalRabbit or any one of these implementations. The key principle behind Metaflow is that it's designed for humans, and humans that have diverse skills and are solving diverse problems. Just take a cross-section of the data science team at Netflix. We have one scientist who has a PhD in physics and studied light coming from a nearby binary star system. We have another scientist who has a political science and government PhD and did some studies around policy making decisions in a collaborative environment. And another person has a PhD in cognitive psychology and did some studies around semantic cognition. So these are very different people with very different backgrounds. And they're also solving different problems for Netflix. Some of the less well-known challenges at Netflix in machine learning are things like, well, what content should we put in our catalog? What content is going to resonate with our members and bring them joy? And there's a lot of interesting work on what would the demand model look like for content that's never been made, that nobody's heard of before. We have challenges around how do we make the streaming experience itself phenomenal? How do we deliver the best bit rate to our customers to give them the best video quality on their device, on their network? And then there's a whole bunch of super fascinating challenges now that Netflix has a studio function as well. For example, we get a lot of scripts coming in, and there's a lot of NLP you can do on those scripts to learn about, how might you organize a physical production around those scripts. For example, automatically highlighting when the hair and makeup person should come on board, or automatically calling out maybe when we might need to look into a legal matter. So there's a diverse problems done by diverse people. What do these people have in common? Well, they need to build models. We require some prerequisite knowledge of all of our data scientists. And so here's the long list of prerequisites. They need to know what a function is, and they need to be able to write a function. So a scientist needs to understand this concept of input, compute, output, and they also need to be able to run a basic script on the command line. This is a little bit basic. Amazingly, though, you can come up with really powerful abstractions on top of this. And the abstraction of choice for Metaflow is a directed acyclic graph, or DAG. And if you've looked at any machine learning framework, you probably have seen this abstraction before, because it's a great way to abstract machine learning workflows that involve batch processes that can take a lot of time. So how would a scientist structure their code using Metaflow? The basic theme is that they write vanilla Python code, and they add a few little decorators so that Metaflow knows what to do with them. So really the first thing that they need to do is they need to extend this Metaflow flow spec class that gives them all kinds of facilities to do all of this DAG stuff. Then they need to structure their code as individual functions and annotate their individual nodes in the graph with this step decorator. And to create the structure of the graph, then they just need to call this self.next method, which creates the arrows in the graph. That's pretty basic. And you might think, wow, that's it? Like there's nothing novel here. There's not really any new ideas here. So on this team, on the machine learning infrastructure team at Netflix, we really measure our success by usage. Are data scientists using this? And the answer is, oh, and I skipped that part. Going back here, all you need to do is run it on your local environment. Okay, so the answer is yes. Scientists are using Metaflow. Oh, no, I skipped ahead. You can also write models in R via a thin wrapper on top of Python. So the incredible thing is that we don't need to rebuild our infrastructure in R. We can actually create this very thin wrapper using a reticulate library. And all of our R users are happy. So we no longer have to worry about this war between data scientists where like, oh, are we a Python shop or are we an R shop? So this kind of resolves that. What about Scala shop? Okay, tomatoes are flying my way already. We can talk about that afterwards. Okay, so anyway, so what's so special about this? Why are we even talking about this? Because it is being used. So we launched our 1.0 internally, and since then we have 134 projects using Metaflow. So something you need to understand about Netflix and why this is relevant is that the culture at Netflix is based on freedom and responsibility. So we hire responsible adults and we trust them to make decisions that are in their area of expertise. So there's no mandate, no VP stood up and said, thou shalt use Metaflow. This is really a testament that it actually is useful in practice. Now I want to get into what would be the day-to-day development experience in Metaflow. The first thing that a scientist might run into is that their job fails or that there's a bug. And so they might need to kind of do a quick development cycle and rerun a particular step in their flow right then and there. And they might need to pull in an engineer when it looks like maybe an infrastructure-based problem. So what they can actually do is resume any step in this flow without waiting for the entire job to run again. Because some of these jobs can take a long time. I mean, in the good case, maybe it's a 30-minute job, but it could take hours. So the last thing you want to do is sit there waiting for hours to try to reproduce your bug. And the reason why you can do this resume step is because Metaflow is backed by an immutable data artifact store, and it's content addressable. So the exact state of the flow at this step B can be reproduced and very quickly, both by the developer on their local environment, but also by somebody helping them remotely. So that's a very powerful feature right then and there that is one step toward kind of reproducible data science. Okay, remember when we talked about Xiaowen and how she needed to get access to compute resources in order to scale her job? With Metaflow, that's very easy and very straightforward. In order to get this compute resources, all you need to do is add this decorator. In this case, we have a plugin for Titus. You could also create a plugin for Kubernetes, and it requests, hey, for this step, I want 16 CPUs and a GPU. Or perhaps you're doing a memory-intensive job, and you need lots of memory. And the beauty of this is you just run it on the command line. Again, you're not leaving your local development environment to get access to these compute resources. What if you need to scale horizontally and you need many different jobs? Let's say you're doing a parameter grid search. Well, all you need to do with Metaflow is set up your parameter grid in this data structure, and you call this kind of self.next method with this for each parameter. And what the for each parameter does is said, for each item in this data structure, create a new parallel task. So the step A over here is going to be instantiated for each item in this grid. So now we get this kind of automatic horizontal scaling. And the real powerful part of this all is this join step, where Metaflow will automatically join together all of these parallel jobs without complicated sort of async logic in there. And one thing that we wanted to look at was, well, how useful is this feature? And it turns out that 40% of Metaflow projects are using Titus. The interesting thing is that many of them are using it within the first couple of days of starting to use Metaflow. And that tells us something really fascinating, which is access to large amounts of compute resources is critical early in the development process of a model. As a data scientist, you no longer have to say, well, I'm going to create this arbitrary smaller data set that's a sliver of the real data set in order to train, and then I get the real data set, and then I get surprised by what actually happens there. No, you can get access to full scale right off the bat. Another challenge that Xiaowen had was getting access to all of her data on these distributed compute nodes. And we've had that challenge too. And we realized that there's a particular access pattern for a lot of these machine learning projects that is different from maybe ad hoc data access in the data warehouse that typically goes through a SQL query engine. We realized that much of the data access is really kind of by the partition level or by the shard level, and these machine learning workflows need access to data in batch. So rather than going through a query engine where you have to submit a Spark job or submit a Presto job, then it does its thing, and then it accesses S3 on the back end, and then it's pulling all that back, and it might run into memory issues or concurrent job issues. Rather, Metaflow provides this very easy way to access a table and access specific partitions of a table, and it will basically go directly to S3, right, using the same Hive metadata as the direct SQL access. So the result is we get 10 gigabits per second, and we're accessing data at speeds that are very difficult to achieve through these SQL interfaces. Now let's talk about deployment, because we can't just build our models, we need to get them out there. And we want to, first of all, like Xiaowen ran into, she needed to schedule her jobs, which meant she needed to kind of take her job and then map it onto this job workflow or scheduling service. Well, Metaflow will take care of that for you. So what Metaflow does is it already knows the structure of your DAG, and it can map it onto the job scheduler DAG interface. It'll create the configuration. So it's very easy to do this directly on the command line. So again, all of that reading of documentation that Xiaowen had to do, she no longer has to do it. And we also wanted to know how many of our workflows get into production. And it turns out about 1/4 of them get into production, which in a research-oriented environment isn't too surprising because you're going to have a lot of ideas that fail. But the amazing thing is within a week, the vast majority of these projects are getting their first run in production, which means as a data scientist, you can figure out what are the production issues your job might run into right after you start developing it. And so that's going to shorten that 4-month development cycle considerably. We also have an interface that looks at your job metadata that you can easily pull up in a notebook. So Netflix uses Interact for notebooks, and you can actually look at what are all the runs of all your flows, and you can even look at the data that was in your flow at a particular point in time. So you can access this immutable data store. So in this case, we had this step that had X as a value. At that point in time, it had a value 0. And sometime later, we had this step X, or this data value X, and it had a value of 2. So we can get access to the exact state, which again, reproducible data science, getting you toward that. Xiaowen's final step was getting her model into a web service. And we've once again made that easy with Metaflow. So Xiaowen doesn't have to worry about like any of the intricacies of REST, how to provision, how to deploy a web service. All she really needs to do is implement this class that says, hey, here's a web service spec. I'm creating a microservice here. And she needs to put her calls to her REST endpoints in there, implement them as functions, and then Metaflow will create this endpoint and she can hand it off to her web app developer. So that was a very quick tour through Metaflow. You know, we've been taking this very human-oriented approach, and so far it's been working well. But I will say that we have a lot left to do. There's a lot of work to do kind of to complete this developer life cycle for models. Much like in the last 20 years, we've spent a lot of time thinking about what the software development life cycle is like. I think that's the big challenge for data science coming up. So I want to just end with a special thanks to Ville Toulos, who gave a very similar talk at QCon a couple weeks back, and he created much of this material. So I think there's time for questions, and if you don't get your question in, then I'm happy to answer them. I'm going to be at the Netflix booth a little bit later. Yeah?
Does Metaflow tell you about the cost of executing the job, and how do you manage, like, how do you prevent data scientists from just running ad hoc jobs?
Oh, I love that question. So the question was, does Metaflow tell you what your jobs cost? The answer is not yet, but that's definitely on the roadmap. Interestingly enough, what I find is that scientists are actually more worried about being too expensive when they don't have to. Like, hey, I'm going to use this compute resource, and it's going to cost $5,000 a year. And like, you know, if you think about how much a scientist costs, that them spending the time worrying about this $5,000 over the course of a year, assuming their job actually runs for a year, you know, it's not actually effective. And we found that so far with these 134 projects, the cost of data storage is actually considerably low. So it's not a concern yet, but that's absolutely something that we'll want to build into the platform. Yeah.
Yeah. So with Metaflow, the only way to deploy your models is via REST API.
So the question is, with Metaflow, is the REST API the only way to deploy your models? And the answer is no. There's quite a number. Most projects actually don't use the REST APIs. So again, with creating a job, you can create any number of different types of artifacts, right? And you have that freedom and flexibility to do so. So in some cases, your job might do some bulk scoring, and it's going to produce a table, and that table is going to be consumed by, let's say, a dashboard, for example. So there's all kinds of flexibility for creating other types of artifacts. Saw a question over here.
So how does Metaflow scale in terms of data set, and also how do you transfer data between stages in the execution graph?
Yeah, so how does Metaflow scale in terms of data set, and then how do you transfer data between those steps? So in terms of, is there a more specific aspect of scaling the data that you have in mind? The data size? Like I said, it's interesting because there's quite a diverse variety of projects that are not like, you know, massive data. size. And usually the bottleneck is actually just the speed of loading the data. And so we haven't yet hit that kind of upper limit on like how much data we can handle yet. But I'm excited to hit those use cases in 2019. And then the other question was, how does Metaflow get data between the steps? I'll save the details for offline, but the immutable data artifact store comes into play there.
Are you thinking about a federated model, actually, where in future you might need to get data from different distributed regions, actually, and then consolidate them? So this is like more or less centralized.
Yes. So the question is, are we thinking about a federated data model? So you might be thinking about the fact that, well, Netflix is a global scale company, and Netflix operates in AWS regions across the world. A choice that's been made up until now is that the data warehouse itself is living in one region. And so I think we would have to evaluate, a lot of these use cases are not necessarily like real-time use cases. And so at this point, we haven't seen the benefit of federating it across regions. So it looks like I'm out of time, and happy to answer questions. I'll be at the Netflix booth. Thank you all.